go. So here we go again. Last time we started talking about principal components and the best low rank matrix. And if you remember, we kind of had some heavy stuff. And mainly, the heavy stuff came from the fact that we had to define what is the norm of the matrix. So I will repeat the basic ideas, the principal ideas on principal component analysis, and I'll go forward with a couple of applications. And this couple of applications will help us understand more deeply the meaning of the magnitude or the norm of the matrix. So we said that the principal components of a matrix A are its singular vectors. And these singular vectors, they represent the columns of two matrices which are orthogonals, U and V. The main idea is that PCA uses the largest U's connected to the first column in U and V to understand the information in the matrix of data, and the data matrix you have. To do what? To obtain an approximation matrix AK, the SVD formulation, which is the best rank K approximation to it. Okay? So, in fact, AK solves what we call a matrix optimization problem, which optimization problem that finds the shortest distance between a K-ranked matrix and our data matrix A. And for example, in statistics, guys, I think you did at least one course of statistics. You are interested in finding the largest variance, so the largest correlation between variables. In our linear algebra approach, we try to find the largest component of a matrix that could represent the whole data. So, in fact, SVD is at the center of data science as a principle, because this is what we call unsupervised learning. So, on the other hand, when the learning is supervised, we have to define a function that helps us classify samples on some training data to provide some learning and decide afterwards to which class our sample belongs. Okay? So, as a reminder, Eckhart said that AK represented the closest matrix to A than any matrix B with rank K. And here are three main choices for the norm of a matrix. We said that is the L2 norm, which is the optimization problem we talked about. Okay? And we will understand what the sigma 1 means here. In fact, it means here if your matrix A has been written using the SVD, then sigma 1 is what? In this case, is always the largest singular value. The Frobenius norm, on the other hand, writes the magnitude of the matrix as the square root of all the singular values, while the nuclear norm writes the same formulation but without square root. Okay, so for example, if you take the I matrix, the identity matrix of rank n, of size n by n, you can find that the L2 norm is 1, because, well, the highest singular value here is going to be the highest and unique eigenvalue, which is 1. While if you sum up all the singular values, I mean all the eigenvalues, here you're going to get n, and you take the square root, and the nuclear norm gives you n. Okay? So the same thing happens, in fact, when you multiply by any orthogonal matrix. What is an orthogonal matrix about? An orthogonal matrix is a matrix such that Qt times Q equals I. Okay? And we say that this matrix is orthogonal. So what is particular to orthogonal matrices is that they kind of keep the magnitude or the norm of the matrix intact. Okay. So for example, we said here if you replace I by any orthogonal matrix K, and the norms stay the same because all the sigma i's are. Okay. So I've been through this before. So I will continue forward. I'll skip this part. I will come back to it, inshallah. Okay. Now, what I'm interested with is to talk about the methodology behind the applications on how to apply the principal component analysis. So we said that let us suppose we have n variables that characterize our population, and we have like n samples or n individuals, and we've taken the height and weight in the population. So we obtain, in fact, the data matrix we call A. And if you subtract from every entry in every row the average of the corresponding row, let's say the average height, MH, is subtracted, and the average weight, you obtain what we call the centered matrix A0. Okay, of course, in many cases, we are talking about a very large matrix. But here in our case, here in our example, we'll be working on very small matrix. So if you subtract that mean from all the M entries in the row, we obtain a centered matrix. And there are also crucial quantities we call variances and covariances obtained from where, if you do just the simple multiplication AAT, you obtain the various covariance matrix, in fact. Okay? So we said that S is the covariance matrix, which is given by AAT divided by M and so on. So in our case, in our example here, we have this matrix, which is centered. So this is the A0 for in our case. And what we did, because you see negative values, what we did is that we removed the average on every column. And if you compute the covariance matrix, you obtain this beautiful symmetrical matrix. And by the way, this variance covariance matrix is always symmetric and always square. Right. Now, if you work on S, what do you obtain? You obtain two eigenvectors, U1 and U2, and two beautiful, of course, A corresponding eigenvalues. Okay. So what does the Eckart-Young theorem say? It said that the first U1, the first singular vector, or in case we are talking about S, the first eigenvector you obtain, represents the closest line to your data set, the one that goes that is the closest to the scatter points you have. So the eigenvectors of S, in fact, represents, as we've seen in the SVD in 1.8, the left singular values of A. While the second Okay. Okay, do you guys now? Hello, do you hear me, guys?
Yeah, now we can hear.
Yeah.
Okay, so I was saying that the singular vector U2 will be representing the second eigenvector U2 will represent the second singular vector of the matrix A. So in our representation here, working on S, we obtained two eigenvalues, 57 and 53, and their sum is in fact the trace of S. With the corresponding eigenvector U1, you can see that the first chunk we obtain, the matrix A1 here, which is written this way, is quite close to the scatter points we have on our Cartesian plane. Okay? And moreover, if you take the first eigenvector here, or first singular vector, left singular vector from A1, and you take the slope that it generates, you can see it represents the directing vector of your line. Okay? Which is quite interesting here, because this gives us many ideas. The first idea is that how can we extend this to other dimensions? Okay? Do you hear me well, guys? Because Abdurrahman is saying that he can't.
Yes, we hear you.
Yes, clearly.
It's clear now.
Okay, so let's see a second application. The critic about the first application that we were able to find the line that goes to be the closest, or kind of the least square approximation to our scatter, but in fact, this might be not the right way to do these things. Okay, so we are saying here that the previous example allowed us to understand the relation between the direction vector U1 and the scatter plot. However, it is considered as a computational mistake to work on the variance covariance matrix using the SVD instead of working on the center data matrix itself. So in our case here, we are taking data from a small startup company where we have two rows. The first row indicates the number of years of experience for each one of the employees. And the second row represents the monthly salary of each one of the employees. And of course, we are trying to analyze this data. And we kind of were able to compute the average number of years of experience, which is most likely 3 here, as you see. And we were able to obtain also the average salary on our data. So if you subtract from every entry on every row the corresponding average, you obtain the centered matrix A0. Okay? So, next we are going to work on this matrix. So in the following, we'll show how to create the left and right singular vectors of A0. So for notation purposes, U1 and U2 are the left singular vectors of principal components of A0. And V1, it's A01. And V1 and V2 and V3 are the right singular vectors. So guys, if we take the A0 we had before here, which is, which size it has, it is, sorry, it's going too fast. It's a 2 by 3, right? So if I do the following, A times AT is going to be a 2 by 2. And this is in fact what we call the variance covariance matrix, right? This is the variance matrix. And the matrix C you obtain if you do ATA, you obtain a 3 by 3 matrix. And remember, what is the goal of the SVD we've seen in the 1.8? The SVD, its goal is to write A0 as U times sigma VT. Okay? Well, the columns in U are what we call the left singular vectors. And the columns in V are the right singular vectors. And the sigma represents the singular values you obtain for your matrices, or the common, in fact, eigenvalues between B and C. So if you do the math here, Shabab, please interrupt me if anything is not clear, please. I don't want to be anyone left without understanding. So if you work on this small matrix computation, Shabab, you can easily find out that you have 2 eigenvalues, 3 and 1. How do you find the eigenvalues? You know this. So you just need to solve determinant of B minus lambda I equals 0 here, and you will have 2 beautiful solutions, 3 and 1. Now, instead of calling them lambda 1 and lambda 2, because we are working on the SVD problem, we call them sigma 1 square and sigma 2 square, for the reason that, in fact, we're going to extract the square roots of these singular values. Okay? Now, if you work on the matrix C and you start looking for the eigenvalues of C, of course, you're going to have 3 eigenvalues here, and some of them are common with B. In fact, you're going to have 0 as a first eigenvalue, and you're going to have the same eigenvalues we had before for B, which are sigma 1 square and sigma 2 square, which is 3 and 1. So the 3 and 1 are the interesting ones we're going to put in sigma. You got it? What I'm going to put in sigma, of course, I'm going to put square root of 3, square root of 1. Okay, so since we have to take the common non-zero, don't forget this, eigenvalues of B and C, which are sigma 1 square 3 and sigma 2 square 1, they are needed to generate the singular vectors. So the 2 eigenvectors corresponding, first of all, to 1 square, which is 3 and 1, give us the two right singular vectors, as we said in the previous lecture, v1 and v2. Okay, we are the right singular vectors. So the ones that we be, in fact, when we are writing A equals U sigma V, so the v1 and v2 will be here. Okay, how did we find them? Because if you go back to C and you place the eigenvalues 3 and 1, you should be able to find the corresponding eigenvectors. So these two, they came from where? From C. Okay, what is C again? C is we wrote as A is 88. So it's 3 by 3. Okay. And from V1 and V2, we can compute easily U1 and U2 using the formulation we've seen, the one that makes the formulation work, that A is equal to U sigma. Okay, so U1 would be AV1 divided by sigma 1. You see here we remove the square. And we obtain this second factor. So we have U1 equal 1 over root of 2, 1 minus 1. And U2 is equal to 1 over 2, 1, 1. And you can easily check that both vectors V1 and V2 are orthogonal. If you do the dot product, the Cartesian product here, you get 1 minus 1, 0. And here if you do U1 times U2, also you get a 0. So the two vectors V1 and V2 are orthogonal. They do have also a unit norm, and we are prepared to continue. So basically here we're able to find the sigmas in capital sigma, the u's and the b's. So we are able to write our first chunk, the first rank 1 approximation of A, which is given by sigma 1 TD. So this very important matrix is in fact the best rank 1 matrix approximation for our A0. Okay, and if you compute the second matrix A2, which is given by sigma 2 U2 V2, what do you obtain? You obtain the fact that the sum of the two matrices U1 plus U2 is A1 plus A2. So if you sum up, you see that you get exactly here the matrix A0. What is beautiful with this is that you can also see that the distance from A0 to A1, once you wrote this, that A0 is A1 plus A2, so A0 minus A1 is just A2. So the distance between A0 and A1 is just the magnitude or the norm of A2, which you could see as the sum just of the item squared. Okay? If you think of it, it's very easy to compute here. If you take matrix A2, you just take every item and you square it and take the square root, so it is 1, which is in fact equals to ln 2. In fact, Eckhart said that this has always to be larger or equal than ln 2, than lambda 2. Okay? Type. Now, do you have any question on this problem, Shabab, or any critic? Is that clear for everyone? So we were able for our matrix A to find the best rank 1 approximation to it using singular values and right and left singular vectors. Okay, so now this was a problem which is quite limited because maybe experience and salary are not the only, let's say, criteria or features needed to describe the data. And many of us know about it. So we kind of here in the third application trying to extend this problem, and we try to dive a little bit deeper into the analysis. So this last example is the experience and salary application to include age and gender as well. So here we've taken the data from 10 employees. And we have in the first row, as usual, the number of years experience, the salary, the age, and the gender. Here, -1 stands for a female, 1 stands for a male. If you do the same analysis as in example 2, we can here see, of course, this is a what? This is a 4 by 10 matrix. And if you do the variance-covariance matrix is going to be 4 by 4. The other one, so is 4 by 4, and C is 10 by 10. And if you take the common eigenvalues between these two, you obtain the 4 common eigenvalues between B and C, and the corresponding eigenvectors from C. You obtain, of course, the most important thing is the first left singular vector. Now let me say, the SVD analysis here, yes, go ahead, Ahmad.
Doctor, what is the left singular
Can you
value?
repeat this?
What is the left singular?
The left singular value, what are they? Can you repeat?
I mean, what is the left singular value represents here in after we find it from this beautiful matrix?
Okay, there is no left singular value. We say left singular vector. Okay, let me share with you the whiteboard. In fact, with SVD, the goal is to write any matrix which is even, non-symmetric, non-square. We write it as U times sigma VT. And this is something important we have to master in Math 405. Okay, so the columns in U here, Abdulaziz, are the left singular vectors. Maya?
Yes, yes.
Okay, and the columns in V are the right singular vectors, where are here. Singular, again, singular vectors. Right. Now, what is in sigma? Sigma has singular values. So we don't talk anymore about eigenvalues, because the definition of eigenvalues and eigenvector doesn't apply to non-square matrix. And in general, we said we are talking with data which has many columns, because you have a huge number of samples or a huge number of individuals in your population, but a limited number of features. So either it's a very large thin matrix or a very tall thin matrix. I'm talking about A. So A is not square. So that's why we cannot talk about eigenvalues and eigenvectors. We talk about singular vectors and either left or right and single values. Are you with me, Abdulaziz?
Yes, yes.
Okay.
So the square matrix is
We've seen we've seen previously how to generate these singular vectors. The singular vectors, you obtain them from AAT and ATA, and the entries in the sigma is a diagonal matrix where you have the singular values, which are the square roots of the common eigenvalues between C and B, as we present. Okay?
Yes.
Okay, Abdulaziz? Right. Thank you for asking. I'm pretty sure many had questions, but they didn't ask. So let me go back to my application. So in this case, where are we? We are here. Yeah. Okay. So we were able to obtain the largest, the one which corresponds the left singular vector, which corresponds to the largest singular value, which is 7.5 here. And the 3 remaining, I'm listing them also, are here. Okay? But one can observe here, what do you observe, Shadab, when you look to the left singular vector? So the first 3 entries are kind of given the importance of the 3 first criteria, which are what? Number of years of experience, salary, and age, right? What about gender? You see, it's very small. This entry is very small compared to the previous ones. Okay? So one can observe that gender does not seem to bring much information from the first left singular vector. So this entry is relatively very marginal, which gives us an idea to remove this Yes, Firas.
Can I obtain the same information from sigma 4?
From sigma
4.
From 4, no, sigma 4 is going to be different. So I can show you the.
No, here you saw the fourth component of the left singular vector, and you decided that the gender doesn't provide much information. So can I obtain the same?
In fact, what I did,
the fourth singular value?
Yeah, in fact, what I did, ya Firas, is that I computed, first of all, the variance-covariance matrix, okay, which is a 4x4 matrix, okay? And I've seen that there is a very small correlation between the gender and the salary, in fact. If you take the variance and the covariance matrix, there is a very small correlation. Here I can show it right now to you. And I will share the Python code with you, okay? So, but here the entry of this is very small. So whenever you're going to multiply by sigma 1 and v1, whatever happens, this is going to be staying very small, okay? That's why I had the idea to remove this complete row. Yeah. Did I answer your question?
Somehow, yes. But I'm saying that looking at sigma 4 only, can I decide that gender is marginal?
Yeah, the gender, of course, yeah, Firas. In fact, what we are doing, we're writing A as A1 plus A2 plus A3, A4, right?
Yes.
So most of the information comes first from A1, hello? Then A2, then A3, then A4. Okay? Of course, the more information you add, you're getting close. When you add A4, you just sum up the 4 matrices and you get exactly the same information. But this is not what we want to do. We want to kind of look for the principal components of A. So most of the information, first of all, comes from A1. So basically, it comes from U1 and sigma 1, as you see. And you can see that from U1, I have a very low impact of gender on my salary. You got it? So if you're looking for a rank 1 or rank 2 approximation for A, by the way, A is a rank 4 matrix. If you're looking for a rank 1 or rank 2 approximation, gender doesn't have any importance, or almost. You get my point?
Yes, yes.
Okay. Sigma 4, of course, the sigmas are ranked in the descending order. And of course, the sigma is going to be the last ones are going to be the smallest. So what I did, Firas, is that I removed the gender, and look what I did. I removed the gender, I removed, of course, the third row, and I worked on my data. So I'll be sharing with you what happened, okay? So what happens with this is that when you remove, of course, here I'm given exactly the continuity of the first thing. So this is the closest chunk, the closest rank approximation to our A0 matrix. And if you remove the gender vector, you can see that regardless of the gender vector, we may now think of the best way to approximate the data. So you are working basically on a 3x10 matrix. And now you can obtain the new singular vectors, which do not have 3 components, but do not have 4 components, they do have 3 components. One corresponds to every feature you have. Okay? So let's see, first of all, what happens computationally. I'm going to share with you the Python code. Okay, so hopefully everyone is going to be able to see this. Okay, so what I did here, Shabab, so I'm following step by step. Here you see that I entered the A0 matrix, the data matrix. Okay, now what I did in the next step, I computed B, which is ATB. And this one would allow me, this is in fact the variance covariance matrix. And this one would give me the left singular vectors. I computed also AT, and as you see, I was able to extract the eigenvalues of B and C and the eigenvectors. Okay? Now, what I'm interested with is to look for the common singular eigenvalues between B and C, and pick the highest one in some order to be able to get the approximation. So let's run it and see what happens, Shabab. Okay, so what happens is, of course, I'm expecting the first computation to give me the eigenvalues and eigenvectors of B and C, and to detect the common eigenvalues between B and C, and to use the common eigenvalues to generate the right singular vectors from V, and then to use them in my computation. Okay, so in fact, I have a surprise for you. I added this plot. Are you able to see each other? So in fact, what you see in front of it, what do you think here? What do you expect? The dots, the green dots, Shabab, are the points of my data. Okay, and what is the plane which is standing sliding perfectly between these points? What do you guys see here? I'm going to just put it right on the right position again. What do you think?
This is the best first rank matrix.
Yeah, exactly. This is the plane which is suggested by the best first rank matrix. And you see that it kind of slides perfectly between the points of my data. Now, how did I obtain this? Well, it's quite easy. So if I go back to my computation here, I have many entries, but I try to detail them. First of all, you have your A0 matrix, beautiful. Here, this is the matrix which is a 10 by 10, which is the matrix which is obtained when you do ATA. Okay, and I have, of course, 10 eigenvalues. Most of them are zero, as I checked, but the last 4 are interesting, are non-zero. So I have kind of 1.25, 568, and 5.7. The last 3, I'm sorry for this. And from these, I can extract the corresponding eigenvectors. Now, C is the ATA matrix, the AAT matrix, which is the variance covariance matrix. I have the eigenvalues. You see the eigenvalues 125, 568, 857 are common with the previous matrix. 57, you see 568, 125. So these are the common eigenvalues between B and C. You agree with this, Shabab? So the 3 eigenvalues I obtained when I did AAT are common with B. Now, I use these eigenvalues to detect the eigenvectors from ATA, which would help us find the rank, the A1 matrix, A2, and A3. So these are the corresponding eigenvectors. I extracted them just by using simple multiplication. Okay, I listed them, and I was able to compute the square roots of eigenvalues to obtain what I call the sigma, the singular values. And I did what? I computed here each one of the vectors U1, U2, and U3 using the V1, V2, and V3 obtained, using the formulation that every vector UI is equal to A times VI divided by sigma I. Okay. Once I did that, I was able to obtain the 3 estimating matrix A1, A2, and A3, which are here, and these are the 3 matrices A1, A2, and A3. Now, the characteristics of that plane I was able to see in my figure, they come from where? They come because what is particular to this plane is that it has 2 main vectors, which are U1 and V1. Do you agree with this, Shabab? Yes or no? So let's suppose you have 2 vectors in that plane, U1 and V1. How do you find the Cartesian equation of that plane? You can use the simple cross product, صح? And if you use the simple cross product, you obtain the Cartesian equation of the plane. And this is exactly what I was able to draw here. Using the Cartesian equation of the plane, I was able to draw this. Okay, so if I go back to the slides, I'm explaining what we did. The mouse is stuck. Okay. So we're going to the last part here. So once we obtain the vectors u1 and u2, okay, and u2 and u3, here we did that. Okay. Now, if we perform the cross product u1 v1, should be v1 here. I'm sorry for the mistake, Shabab. You obtain the main values here, A, B, C. That makes you write the Cartesian equation of your plane. Of course, this plane should go through the point 0, 0. Why through the 0, 0? Because the point 0, 0, which is T0, represents the point which is at the center of the data matrix. And you can see that we were able with Python to get a very good linear approximation using a plane of our scalar data. Well, this gives many ideas. The idea that now if Z corresponds here to the salary you might give to an employee, if you know the age and the number of years of experience, you can already set the salary. They approximate the salary that you could allow to this employee. Okay. Any questions, Shabab, before I take the attendance?
Yes. How to delete the unnecessary attributes systematically? So how can decide that this feature is irrelevant here? You mentioned that you can see the fourth component, but it's not systematic.
Okay. Beautiful question, Firas. Thank you for asking. So that's what I promised you. So I promised you to show you how to work on the sorry for that. How to work on the fold data, right? I'm gonna show you how to work on the fold data. Hopefully it's gonna work. But, just be patient with me. Okay. I'm sharing with you the same thing now based on okay, it's okay. So here I have the data, Firas, which includes the gender, as you see. Are you okay with this? Right. So let's see first of all what it gives as a variance covariance matrix. So remember here that the gender was the fourth item. Oh, there was a mistake. Okay. Anyway, Firas, the idea is that when I was computing the variance covariance matrix, I had a very small variance between salary and gender. So I was able early on to detect that gender has almost no impact on the salary. So it's a kind of irrelevant information. Another way to see it is when I saw, as I said in the slides, the fourth component of my first and most important singular left singular vector. Okay, Firas?
Okay.
He have a computational problem, but I was just willing to show you the various covariance matrix. That's it. Right. So let me quickly please take the attendance. Or everyone is here, so no need for it. So guys, do you have any question? Hopefully this gave a whole picture about the importance of SVD, inshallah. And I will post the, I already posted the slides. So I'll post the corresponding Python code so you could run it and see how the plane slides perfectly within the 3D scatter plot. Any questions, Shabab?
Also, don't forget to upload the first Python code, scatter one.
The one with the height and weight?
For the first example, yes, height and weight.
Inshallah. Right. Thank you very much, Shabab. Don't forget, so I sent to summarize what we discussed at the beginning of the session. Inshallah. Anything else, Shabab, before we leave?
Doctor?
Yes, Khalid.
Can we delay the major to the next Saturday? Because on 8th of October we have a major.
Okay. We said the 10th, right?
Yeah, can we make it on the 16th?
16. So from 10 plus 7, 10 plus 7 is 17, right?
Yeah, exactly, 17, sorry.
I don't know what the guys think.
We have no problem.
You have no problem. You will have no problem. Fine. Okay. So we will discuss it again next time, Shabab. Till then, I hope you have a WhatsApp group and things like this, and you can agree on date. Come back to me with a convenient date. Okay? I have no problem. Okay. طيب. See you, Shabab. يلا. السلام عليكم.